Welcome to our material science course. This course is designed to provide an in-depth understanding of materials that are fundamental to electronic devices and systems. Material science plays a crucial role in technological advancements, affecting the efficiency, durability, and capabilities of electronic components. Over the next chapters, we will explore different material classifications, atomic structures, and the relationship between material properties and electronic applications. By the end of this course, you will have an understanding of how materials shape the world of electronics. Before we dive into specific materials, let's establish a solid foundation. Material science is the study of the properties and behaviors of materials which are used in various engineering applications. These properties determine how materials respond to external forces, temperature changes, and electrical stimuli. Engineers must understand how materials interact to select the best material for a given application. This course will focus on electronic materials such as conductors, insulators, semiconductors, and magnetic materials. Our course will be structured into several key topics. First, we will cover the basics of material classification and atomic structures. Then, we will explore the properties of conductors, insulators, and semiconductors. Following this, we will study magnetic materials and essential electronic components, including resistors, capacitors, inductors, diodes, transistors, and transformers. By understanding the materials behind these components, we can optimize their performance in real world applications and advanced topics about material science. So let's get into the course with an introduction. Materials have played a defining role in human civilization. We often categorize historical periods based on material advancements, such as the Stone Age, Bronze Age, and Iron Age. In modern times, we have entered an era dominated by advanced materials like polymers, semiconductors, and nanomaterials. Silicon, for instance, is a fundamental material in electronic devices, leading to what we call the Silicon Age. By studying material science, we gain insight into how materials shape technology and everyday life. Metals, particularly steel, are among the most widely used engineering materials. Steel exhibits several key metallic properties. It is strong, ductile, and an excellent conductor of electricity. These characteristics make it a preferred material for structural applications such as bridges, buildings, and electronic circuits. Understanding the behavior of metals at the atomic level allows engineers to improve their strength, corrosion resistance, and electrical properties. Unlike metals, ceramics such as aluminum oxide have distinct properties that make them valuable in engineering applications. Ceramics are chemically stable, have high melting points, and can withstand harsh environments. This makes them ideal for applications such as insulators and optical coatings. A key distinction between metals and ceramics is that ceramics are generally brittle, meaning they break rather than deform under stress. Glass is a unique material with properties that differ from both metals and ceramics. While it shares the brittleness of ceramics, it is amorphous rather than crystalline. This gives it important optical properties, such as the ability to transmit visible light. Glasses are widely used in display technologies, optical fibers, and protective coatings. The ability to manipulate glass composition enables engineers to develop specialized applications, such as UV resistant coatings or glass panels. Polymers are one of the most revolutionary material classes in modern engineering. These long chain molecules are typically lightweight, flexible, and inexpensive to produce. Nylon, for example, was initially developed as a replacement for silk and became a critical material in World War II for parachutes and military gear. Today, polymers are found in nearly every industry, from consumer electronics to aerospace applications. Semiconductors are the foundation of modern electronics. Unlike conductors and insulators, semiconductors have an intermediate electrical conductivity that can be controlled through doping. Silicon is the most commonly used semiconductor material, enabling the development of transistors, microchips, and integrated circuits. The ability to manipulate silicon at the atomic level has led to rapid advancements in computing, communication, and sensor technology. Material science is deeply connected to physics, particularly solid state physics. The behavior of materials is governed by principles of classical and quantum mechanics. For instance, the electronic properties of a material depend on its band structure, which determines whether it acts as a conductor, insulator, or semiconductor. Engineers must understand these physical principles to design better electronic components and materials with enhanced performance. As depicted in the diagram, solid-state physics is positioned between classical and quantum mechanics. Classical mechanics governs macroscopic motion and forces, while quantum mechanics explains the behavior of particles at atomic and subatomic levels. Solid-state physics combines these principles to describe the behavior of materials, particularly in terms of electronic, optical, mechanical, and thermal properties. This field plays a critical role in designing and optimizing electronic materials used in semiconductors, insulators, and conductors. While quantum mechanics dominates the behavior of electronics in solid materials, relativistic effects become significant at high velocities, particularly in advanced materials such as graphene and high energy particle interactions. The figure highlights how relativistic mechanics extends beyond classical mechanics and how relativistic quantum mechanics plays a role in understanding high-speed charge carriers in electronic devices. At the microscopic level, electronic materials science investigates complex spatial lattices composed of atoms, ions, or molecules. The forces acting between these particles are predominantly electrostatic in nature, meaning that interactions arise due to electric charge distributions. This understanding is crucial in the study of semiconductors, where the movement of charge carriers is fundamental to device performance. Solid-state physics act as a bridge between classical and quantum mechanics, describing how atoms interact within solid materials. Although an atom is electrically neutral, its charges are not concentrated at a single point. Instead, they are spatially dissipated, leading to both attractive and repulsive forces when atoms come close together. This balance of forces determines the structural stability of materials and influences their electrical, optical, and mechanical properties. From a classical mechanical perspective, an atom appears mostly empty since the electron cloud occupies a vast space compared to the nucleus. However, at the quantum level, these electrons define the material's behavior, affecting conductivity, magnetism, and other properties crucial to electronic material science. Understanding these interactions helps engineers develop advanced materials for semiconductor and electronic applications. Electronic materials, including metals, semiconductors, insulators, magnetics, nanomaterials, are primarily classified based on their electrical properties. The most critical parameter in this classification is electrical conductivity, sigma, measured in Siemens per meter. According to Ohm's law, the relationship between current density G and the applied electrical field E is given by G sigma E. The temperature dependence of conductivity varies significantly across material types. Metals exhibit decreasing conductivity with increasing temperature due to enhanced electron scattering, while dielectrics show an increasing conductivity as thermal energy generates new charge carriers. Semiconductors, however, have an intermediate behavior where conductivity increases exponentially with temperature due to excitation of charge carriers into the conduction band. Understanding these variations is crucial for designing electronic components with stable performance across different operating conditions. The electrical conductivity sigma of materials behaves differently for metals, semiconductors, dielectrics as temperature changes. In metals, increasing temperature causes conductivity to decrease due to enhanced scattering of charge carriers by vibrations, which means phonons. At very low temperatures, conductivity can become extremely high, even reaching infinity in the case of superconductivity. In contrast, dielectrics exhibit an increasing conductivity with temperature as thermal motion generates new charge carriers. However, at room temperature, 300 kelvins, dielectrics still have extremely low conductivity, making them ideal electrical insulators. Semiconductors display an intermediate behavior where conductivity increases exponentially with temperature due to the excitation of electrons into the conduction band, making them highly tunable for electronic applications. The behavior of electronic materials can be understood by addressing two key problems. The first is determining the ground state of solids, which involves understanding the forces that hold atoms together in a lattice. This includes factors such as crystal structure, bonding types, and cohesion forces. The second problem concerns the response of solids to external influences, including electrical fields, temperature changes, and light exposure. These factors determine the electrical, thermal, and mechanical properties of materials. Since studying the ground state requires examining how materials behave under external disturbances, the two problems are interconnected. For instance, an applied electrical field can modify electron distributions, while temperature variations can affect conductivity. Understanding these interactions allows engineers to develop materials with optimized properties for electronic applications. The study of electric fields is essential in understanding charge transfer and electrical conduction in materials. When an electrical field is applied to a solid, it influences charge carriers, electrons, ions, leading to the classification of materials as conductors, semiconductors, or insulators based on their response. Charge transfer mechanisms vary. Electronic conduction occurs in metals and semiconductors, where free electrons move under an applied field. Ionic conduction happens in certain materials like electrolytes, where ions migrate. Electrical polarization occurs in dielectrics, where charge displacement leads to a dipole formation rather than free conduction. Understanding these effects helps engineers design materials for applications in capacitors, transistors, or electromagnetic wave propagation systems, as illustrated in the diagram. Magnetic fields also play a crucial role in determining the behavior of electronic materials. Depending on their chemical composition and atomic structure, solids exhibit different magnetic properties. They are classified as diamagnetism, paramagnetism, ferromagnetism, antiferromagnetism. Magnetic fields are widely used in electronic materials research, particularly for studying charge transport phenomena. Uh, these effects is essential for designing efficient sensors, memory storage devices, or electromagnetic shielding systems. Here are some other key concepts: temperature gradient and charge transfer. Temperature gradients drive energy flow from hotter to colder regions within a solid. Simultaneously, electrical charge transfer can also occur, influencing the material's conductivity and phase transitions. The graph illustrates how phase changes happen at critical temperatures, affecting material structure and properties. Interaction with light and particles. The absorption, reflection, and scattering of light provide insights into the interaction between electromagnetic waves and solids. They are crucial for optical materials. Irradiation by electrons or other particles, or dosed implementation of additives, or doping, Wessels formation, and atomic substitutions are some other key concepts of the topic. Materials are broadly categorized into metals and alloys, ceramics and glasses, polymers, semiconductors, and composites, each serving critical functions in engineering applications. Metals such as copper and alloy steels are widely used in electrical wiring and structural components due to their high conductivity and mechanical strength. Ceramics and glasses offer thermal insulation and high temperature resistance, making them ideal for applications like refractories and capacitors. Polymers, including polyethylene and epoxy, are lightweight and flexible, often used in packaging and electronic insulation. Semiconductors, like silicon or gallium arsenide, exhibit unique electrical behavior, enabling modern electronics, transistors, and optoelectronic systems. Composites combine multiple materials to enhance mechanical and thermal properties. They are seen in applications like aircraft components or reactor vessels. Uh, these applications allows engineers to design optimized materials for electronic, structural, and industrial uses. The structure of materials plays a crucial role in determining their physical, mechanical, and electrical properties. Material structures are analyzed at five different levels: macrostructure, microstructure, nanostructure, atomic arrangements, and atomic structure. At the macrostructural level, coatings and surface treatments enhance corrosion resistance. Microstructure, which includes grain size and boundaries, significantly affects the strength of metals and alloys, with finer grains generally leading to increased material strength. At the nanostructural level, materials like iron oxide nanoparticles are used in ferrofluids for heat transfer applications. Short-range atomic order, as seen in silica glass, governs amorphous materials, influencing optical properties critical for fiber optics. Long-range atomic order, such as PZT ceramics, enables piezoelectric properties used in actuators and sensors. At the atomic scale, materials like diamond with strong carbon-carbon covalent bonds exhibit extreme hardness, making them suitable for cutting tools. Understanding these structural levels is helps to manipulate material properties for specific applications in electronics, energy, mechanical, all of the engineering disciplines. In this chapter, we explored how material structure influences its properties and applications across various engineering fields. Next week, we will deep deeper into atomic structures, exploring how atomic bonding, crystal structures, and electron configurations determine material properties at the most fundamental level. We will analyze how these atomic scale interactions influence conductivity, magnetism, and semiconductor behavior. That's all. See you all next chapter.